NASA STEM Engagement and Educator Professional Development Collaborative logo. Welcome to NASA STEM EPDC Quick Bits Big Ideas in Science Content. NASA STEM Engagement and Educator Professional Development Collaborative provides NASA resources and STEM strategies for STEM engagement. In this series, we intend to reach educators, parents, and caregivers to quickly explain a specific big idea in STEM. We will introduce a NASA example of how this idea is applied in the real world, and finally, we will demonstrate step-by-step how to lead this activity at home or in the classroom with your students. You might invite your students to watch with you at that time. We invite you to join us as we learn more from our specialists. Let's get started.
Hello, I'm Susan Kohler, a NASA education specialist from NASA Glenn Research Center in Cleveland, Ohio. We are going to use a roller coaster activity to introduce students to the scientific concepts of force and motion, along with potential and kinetic energy and the engineering design process. The next generation science standards that align with this activity can be found in the motion and stability and the transfer of energy sections of the physical science standards for grades K through 8. We're going to use the engineering design process. We'll start out by identifying a problem of how to build the best roller coaster we can possibly build. We'll look at the criteria and the constraints for the roller coaster, think about some possible solutions, get some ideas going, and then start to build our roller coaster. After we build the roller coaster, we'll test it and see what we have to redesign. What makes a roller coaster fun when we go to the park? What kinds of roller coasters do we like? Usually, we like a roller coaster ride that takes the longest time possible and at the same time gives us a thrill. What do you know about roller coasters? Have you ridden a roller coaster before? Can you describe the best roller coaster in your own words? Sir Isaac Newton developed a series of laws about how physical forces act together. One of those laws you've probably heard before, that an object will stay still at rest unless it's acted upon by a force. And a force is any push or pull. Gravity is a force that causes things to fall down to earth. You might remember Newton's experiment where the apple fell down from the tree and he wondered, why did it do that? So when something falls to the earth, gravity is the force. So is gravity a push or a pull? It's a pull because things are being pulled down to the surface of the earth. When you think about your roller coaster, you're going to have to consider that force. Everything is going to want to fall to the earth. To increase the amount of speed that you get down the roller coaster, you're going to have to increase the height that you drop the marble from. Let's watch the astronauts on the International Space Station explain kinetic and potential energy.
Video footage of International Space Station with Earth in background. Astronaut Joe Acaba releases ball from elastic band using slingshot motion. STEMonstration's logo from NASA STEM Engagement is displayed.
Welcome to the International Space Station. I'm astronaut Joe Acaba. Today, we're going to talk about potential and kinetic energy. Let's get started. Kinetic energy is the energy an object has because of its motion. An object can store energy based on its position. This is called potential energy. On Earth, imagine dropping an object from a raised position. As an object's altitude above the Earth's surface increases, its gravitational potential energy also increases. The potential energy stored due to its position is now being converted to kinetic energy. We also observe this with elastic potential energy.
Okay, new term. Elastic potential energy occurs when objects are compressed and stretched, or generally deformed in any manner, creating potential energy. Think of this bungee or a spring. Okay, Joe, what's next?
We pull back on the band and create potential energy. When we release the potential energy, it is converted to kinetic energy. Here on the International Space Station, we are still under the influence of gravity, primarily due to our position with the Earth. So when I have this ball on this ramp, normally back on Earth, I release the ball and it rolls down the ramp due to a change in its potential energy that's being transferred to kinetic energy. But as you can see, it doesn't happen here. So it doesn't mean we don't have potential energy. It just means we're not converting it at this time to kinetic energy. And why is that? Gravity is pulling us down, but we're moving super fast. And so what it is we're bending around the Earth in this perpetual falling motion. Thanks for joining me on board the International Space Station. We're sending it back to Earth so you can try your own experiment. See you next time.
Astronaut Joe Acaba floats up out of frame. URL is www.nasa.gov/STEM-on-station.
Questions to consider. What is the force acting on the car of the roller coaster as it goes down the hill? That would be gravity. How can you make the force greater so the car will go faster? You would have to put it up on top of the hill and make the hill higher. When does the car have the greatest potential energy? That would be when it's at the top of the hill. And when is the car demonstrating kinetic energy? When it's rolling down the hill. You want it to be a long ride, and you want the marble to stay on the track. You'd want your people to stay on the track too. As part of the planning process, you should make a sketch of your roller coaster. Let's get started. What materials will you need? First, you will need 3 pieces of foam that insulates pipe that you can get at Home Depot, Lowe's, or that kind of store. Once you get those pieces, they're about 6 foot long, you want to cut them in half. And as you cut them in half, you'll make natural grooves for the marble to roll down. Next, you will need a ball to roll down the grooves as you are making your roller coaster. So probably the best thing to use is a marble if you have a marble. If you don't have a marble, Nerf balls work just as well. Here's a bouncy ball. You could use that. If you don't have a ball, but you have some Play-Doh or some clay, you could make a ball. These balls are not all the same. And how much the ball weighs or its size, do you think that will impact how it rolls down the track? Think about that for a minute and make a decision about what kind of ball you would like to use. Next, you're going to need some tape to tape the track together. You can use duct tape, masking tape, or you may want to use painter tape because it will not take the paint off the wall or ruin the furniture. That may be mom or dad's preferred tape. Whatever you choose, remember this: tape has properties of its own. You may want to find something to capture the marble or ball at the end of the run. This way you won't have to go running after it around the house. You could use a plate like this, or you could use a cup at the end of your run. As part of the data collection, we're going to want to time how long it takes the ball to go down the run. So you will need a stopwatch or other timing device to help you collect that data. Since we are using gravity as our force in this activity, we're going to need some height. You can use anything you have in the house, any furniture at all. Whenever you have a challenge in front of you, it's important to remember what your goals are. For this challenge, we are going to have one initial hill. We're going to have you build an additional hill, a loop, and eventually one turn in your design. Make sure you do a nice drawing of your plan ahead of time. Make sure you record the time it takes to complete the run for 5 complete marble runs. Let's talk about the data that we're going to collect for a minute. This is an example of a data sheet that you could put in your journal. You're going to want to record what trial you're on, whether your marble made it all the way through the run or not, how long it took, and then after the run, the changes you made to the design. Scientists and engineers use a journal when they are doing their experimenting and when they are collecting data. They do this because sometimes your first run is your best run. You make changes and then it doesn't go as well. So you want to remember exactly what you did on the run that worked the best. So what are we going to put inside the journal? We're going to want to make sure we write down what the name of the activity or project is, in this case Marble Run, what date we completed this project or collected this data. Then we want a drawing of the design of the Marble Run that we used to collect the data. And then in your data sheet, we'll record the data of how long it took, whether or not it completed the run, and any additional changes or modifications you had to make as you were completing the run. So this is what happened when we made the roller coaster at my house, and this is how we adjusted it until we could get the marble to complete the run.
Susan drops the ball from the top of the Marble Run track. The marble travels down the insulation tube slope to the first hill, but cannot make it up the hill. It does not have enough energy. Susan adjusts the second hill to have a slightly less steep slope. She drops the marble again, and it still does not make it up the second hill. After the third try, the marble makes it up and over the hill.
How did we do? Here's where you can find the NASA STEM lesson plan for this activity.
PDF image displayed titled Amusement Park Physics with a NASA Twist, followed by an image of the workbook's data and calculations table and students completing the roller coaster challenge.
Thank you for joining us, and good luck with your marble run.
Thanks for watching this NASA STEM EPDC Quick Bit. Don't forget to check out the description below for more information and links. www.txstate-epdc.net. Logos for the Texas State University LBJ Institute for STEM Education and Research, NASA STEM Engagement and Educator Professional Development Collaborative, and NASA Partner. The material contained in this document is based upon work supported by a National Aeronautics and Space Administration (NASA) grant or cooperative agreement. Any opinions, findings, conclusions, or recommendations expressed in this material are those of the author and do not necessarily reflect the views of NASA. Images and footage courtesy of NASA. Images and footage used under licenses from Shutterstock.com and Envato.